Is everything okay, sir? Shall we start?
Madam, you are muted.
Okay, sir. Is everything okay? Okay.
Madam.
Good morning to all. Am I audible now?
Salila madam. Salila
Can,
madam.
can you hear me, ma'am?
Yes, I can hear. Ask HOD to come on to the line.
Oh, I must call him.
Yes, yes.
Okay.
Shall we start or do we need to wait? Can you confirm, please?
Salila madam, start madam. Sir has come.
Yes, ma'am. Good morning to all. I welcome our professor and head, Dr. V. Ambedkar, sir, workshop director. Welcome you, sir. Good morning, sir.
Good morning. Good morning.
I welcome our resource person, Dr. Vishnu Vardhan from Pondicherry University. Good morning, sir.
Good morning, madam.
I welcome all the organizing secretaries, Dr. K. Pravina ma'am, Dr. S. Kalaivani ma'am, Dr. V. Sushila ma'am, and Mr. Jay Prakash. And I welcome all the participants for this program. Now, I invite Dr. K. Pravina ma'am to introduce our resource person. Pravina ma'am, please.
Thank you, Salila madam. Most respected head of the department, distinguished resource person, and my dear learned friends, a warm good morning to you all. Today, the 7th anniversary of our former president, APJ Abdul Kalam. A small quote, I start the introduction with a small quote. The essence of a happy life and a peaceful society lies in one sentence: what can I give? Yes, today we have with us Professor Vishnu Vardhan, Associate Professor from Pondicherry Central University. He has already handled one session for us and now he is with us again to give valuable inputs on Ankova, Mankova and Mankova. Some of his important milestones are: he is a PhD from SV University Tirupati and his guide is a renowned statistician, Professor KVS Sharma. He is a visiting professor to SV University. He is a referee for few reputed and indexed journals. He is the chief editor of Journal of Statistics and Application. He has delivered 60 lectures as resource persons in various workshops and conferences. He is the assistant coordinator of online entrance examination of Pondicherry University for the academic year 21-22. Such a distinguished personality is Professor Vishnu Vardhan. On behalf of the Department of Education, a warm welcome to you, sir. Now I kindly request you to handle the session.
Yes, thank you, madam. Thank you for the introduction.
Thank you, sir. Sir, one more thing I want to say to you. If you need to enable the chat, you yourself can enable the chat whenever you need, sir.
Okay, madam. Yeah, I may expect to enable the chart as soon as I cover some concept by concept, like after Ankova, after Manova, like that. Okay, we'll try to make it so that we can have in between interaction for better clarification. Okay.
Yes, sir. That you also can do, sir, if possible. Okay.
Okay, fine. I'll try to do. If not, I'll
Thank you,
take the assistance of your team. Okay. Yeah.
Yes. Yes. Thank you, sir.
Yeah. So, shall I start the session?
Yes, sir. Sure,
Yeah.
sir.
Yeah. So, very good morning to one and all who are present here. So, again, let's have some discussion on three important concepts like Manova, Ankova, and Mankova. Okay. So, I think in yesterday's session, one of the resource person have given some, good introduction to and a good methodological aspect to parametric test, that is TF and Anova. Now let us try to extend it in a next level of understanding. That is, we'll start with Manova. Okay. So generally there is a broad description, broad categorization of techniques and hypothesis testing. When you have two groups and a single variable under comparison, let us take you have two different exercises, treadmill and cycling, and you want to measure the body mass index after 30 days or after 60 days, then generally we go with the t-test, basing on the certain, what we say, validation of assumptions. Okay. Similarly, when you have, when you include one more group, like treadmill, cycling, and a control group which does not do anything, so then it will become again body mass index will be measured at the end of the 60 days, something like this. Then in that case, what will happen is here, instead of t-test, we'll go to apply or choose analysis of variance, because we have more than two groups under comparison. Okay. So now, hope you have got a basic understanding about Anova with what I have given a small example in yesterday's session. Now, let us try to have a structure, a practical experiment, an experiment in this way. Reconsider the same example, that is treadmill, cycling, and a control group which doesn't do all these things, but they will be on certain diet. All the three groups will be on a common diet. But now, along with body mass index, I'll be measuring their heart rate, okay, their sugar levels, and body mass index. Okay, so I will, instead of one variable, I'll be collecting the data on more than one variable. And I want to compare these, how they differ across three different groups, that is a control group, and a group which is on treadmill exercise, and a group which is on cycling. Now, when we do have three groups and a single variable, already we are aware that we will be using analysis of variance, that is one-way ANOVA kind of a thing. Now, I have added some more information to the experiment, that is, along with the body mass index, I'll be collecting the data on heart rate, and I'll be collecting the data on some other variable, that is sugar levels. Doing so, I'm creating a data structure which turns into a multivariate phenomenon. Now, the structure what I have is a multivariate structure, because I am talking about three variables, and all the three variables are being compared across three groups, that is cycling, treadmill, and a control group. In such a case, can we conduct ANOVA, or do we need to go for any other appropriate test which can support all the three variables at a time? So there we have a technique, an extension of analysis of variance, that is multivariate analysis of variance. In short, what we call is Manova. Okay, in short, what we call is Manova. So here also we do have certain assumptions how we have in Anova. In Anova, what we do, we say that all the observations are independent, all the groups to be distinct, they are mutually exclusive, and data should follow normally distributed. The same assumptions will come in Manova as well, but there is slight change in the assumption that all the data related to body mass index, heart rate, and sugar level should follow multivariate normality. Instead of a normality, we go with a distribution setup. That is what we call multivariate normal distribution. Okay, how to check that? There are quite a good packages we have. Okay, we can check the multivariate normality assumption also. Okay, that is quite easy to do in R programming using MVN package, multivariate normality package. Okay, and like this, we have certain assumptions. Now, how should be my dependent variable, and how should be the independent variable? Okay, now my dependent variable is a vector now, where you take the responses on body mass index, you take the responses on heart rate, you take the responses on the sugar levels. And these are observed, across each group, that is control group, cycling group, and treadmill. Now, in this is with a small introduction of this, I'll take you to an example, very old example, well-established example, which is taken to explain the multivariate analysis of variance technique. Okay, so I request you all to stop giving chat messages. Okay, for meantime, the organizers can disable the chat. Okay, and whenever I require, I can ask you so
Disabled,
that
sir. Disabled.
Yeah, thank you. So now I'll be taking you to one data, that is what we call Egyptian skull data. Egyptian skull data. Okay, there they have the skull measurements. Okay, on 4000 BC, 3300 BC, 1850 BC, 150 AD, and 200 AD. Okay, on different 5 generations of over the years, they have the measurements of skulls across 4 parameters. That is height, breadth, okay, length, and nasal height. Height of an individual, breadth of an individual, length of the individual, and then nasal height of the individual. So these 4 parameters were collected across 5 different years of BC to AD. Okay, another example to take Manova is again well-known famous example called iris data. So most of you have heard about the iris plant example, where you have 3 types of species: versicolor, virginica, and setosa. And these 3 species, the measurements were collected on sepal length, sepal width, petal length, and petal width. Likewise, you can go on like taking 3 products of pens and their point of measurement, the nib measurement, okay, the length of the pen, the diameter of the grip. Likewise, you can take any example that is recorded on more than 2 groups and more than 1 variable stands, and the measurement should be in a continuous way. I mean, the outcome variable, response variable should be of a continuous way. Then we can easily imply or apply the multivariate analysis of variance. Okay, now I'm about to share my screen of this Manova skull data. Hope you are able to see the data, right? Yeah. So now what we do is, this is the variable view. We are into the variable view, and you have a breadth, height. This is breadth, height, length, and nasal height. And in here, if I take this on value labels, you can see 150 AD, 200 AD, 1850 BC, 3300 BC, and 4000 BC. Okay, so now if the data is ready, let us go to the data view. Let us go to the data view. See, these are all the measurements. I think I need to create a decimal part. Okay. Now, the first and foremost step is to let us try to compute the mean and standard deviation. Okay, how to do that? Analyze, descriptives, and then descriptives. I'm trying to show you one thing where we should not do in such a way. Now, doing so, I want mean and standard deviation. But how to generate the mean and standard deviation according to my requirement also should be made well in before. Do you need just mean and standard deviation, including all the samples? I mean, all the years data? Then choose this. Now, can we conduct mean standard deviation for a nominal data? No. Okay, it doesn't make sense. So remove that nominal variable. And then consider only the continuous data, that is measuring data, and go to the option. By default, it will be checked in with mean, standard deviation, minimum, maximum. If you want to check for the normality for each independent variable, you can select this kurtosis and skewness. So skewness should be 0. Okay, if the skewness is almost near to 0, then data is quite normal. Okay, that is not my concern now. Okay, now we have selected and click OK. So doing so, what we got is we got the mean breadth, mean height, mean length, and mean nasal height of total generation data. I mean, this 150 samples include 150 AD, 200 AD, 1850 BC, 3300 BC, and 4000 BC. So all 5 different years data, total mean is this. But this is what I don't want. I want that under each year of data collection, how the breadth, length, height, and nasal height has its average response. That I want. I repeat again. I want to know how these characteristics, that is breadth, height, length, and nasal height, has the pattern over the different years. Then how to get that? That is a very easy thing. Let us do it in a different way. Analyze. You have compare means. Okay, yesterday we might have seen this pop-up, right? In doing independent sample t-test, paid sample t-test, Anova, you might have chosen this particular pop-up. In a similar pop-up, you have another option called means. This is what called analysis of means. Okay, click on this. Now, what is independent? What is independent? Independent is year. The categorical information will become year, and all the measuring characteristics will become the dependent list. Why they become dependent list? Because across different years, the measurements do vary. The measurements do vary. That's why we take year in the independent list and select all the variables into the dependent list. Okay. Now, options. By default, you will be having mean, number of cases, and standard deviation. If you want to add minimum, maximum, range, variance, kurtosis, anything, these many statistics measures are also available. Like standard error of mean, something like that. You want to take some of that, you can take. But as of now, I am interested to look into only mean and standard deviation. Mean and standard deviation. Now, already by default, it is in the cell statistics pan. I'm clicking on the button continue and then press OK. Okay, we got the mean and standard deviation across different years of data collection. Now, let me restructure this data as table. into some meaningful thing. Let us take the pivoting throws, and I want to make the statistics on this particular thing. Okay, or yeah, like this. Okay, or I can transpose it better. I can transpose the rows and columns, and I'll do this. Yeah. So this is what I got. Let us try to remove this n. We can edit, we can remove. Nothing wrong. Okay. I'm able to remove this, and still I can make it more comfortable like this. Okay. Okay, let me do like this. Okay, this was meaningful. This was more meaningful. Okay. Now, in 150 AD, the mean breadth was 136. And over the years, there is a the average breadth of the human, okay, increased gradually from 4000 BC to 150 AD. Okay. And similarly, if you take the height short, slightly decreased. Okay. And if you observe the length of the body, okay, length of the skull, it gradually decreased over the years. What about the nasal height? Doesn't much vary, doesn't do much vary here. Now, with this example, let us do one thing. Suppose I have only nasal height to be considered, and across that to be compared across the years of data collection, then that will become one-way Anova. Okay, I repeat again. If I consider only one variable among these four, then that will reduce to one-way Anova. If I consider two, thereafter we have to use Manova. More than one variable to be compared across several groups will be with Manova. Now, what is the hypothesis that covers here? Basing on this, one second, basing on this, what is the hypothesis that we take into account? The average breadth is similar, will be same across the different years. That is the first hypothesis. Second hypothesis, average height will be same across the years. Similarly, length, similarly, nasal height. We'll get four hypotheses: null hypothesis and alternative hypothesis. What do you mean by null and alternative? In null hypothesis, we'll try to establish a statement, a claim that there will not be any supportive evidence to distinguish between the mean breadth or mean height or mean length or mean nasal height across the different years. See, the statistical inference or testing of hypothesis, what we do, will create an evidence to have a proper claim whether to accept or not to accept the statement defined in the title of hypothesis. Okay. Again, whether to accept or not to accept purely depends upon the level of rejection. When you take the level of rejection into consideration, that is what we call type 1 error, or in notations we call it as alpha, 0.05 or 0.01. Okay, so 5 out of 100, you will be trying to accept the null hypothesis even though it is not being accepted. Okay, so this is one sort of a simple example, understanding what we can have. Generally, I have a simplified notion of remembering the steps in hypothesis testing. Okay, I'm not talking about estimation. This is what we did. We have estimated the means. we have estimated every time in a total statistical inference part. First, we need to estimate the means and use the estimated means and then go for hypothesis testing framework. Okay. Now, I was telling about this means, right? Now, the 5 important steps which will be in our hand is nothing but the null hypothesis, the alternative, the level of significance, the test statistic, and the inference part. So null hypothesis, alternative, level of significance, test statistic, and the inference that we draw based on the p-value or a table value. So it's quite easy to remember. Whenever a data structure is given to you, you need to have a memory that, yes, given a data structure, I want to compare a particular characteristic across groups. First, I need to define it as a null hypothesis. That is, there is no mean difference. Okay, I repeat again, there is no mean difference between the nasal height across the ears. There exists a mean difference between the nasal height across the ears. Now, to validate this, I need a level of rejection that I choose it as 0.05. Now, since I am considering only one variable at hand as of now, and I need to compare that nasal height across the ears, I use one-way Anova. Okay, one-way Anova table will be generated. Now, once I do that, basing on the F value and P value, I'll try to inference whether I need to go with the H0 or I need to go with the H1. Similarly, now I have 4 variables at hand. Now I define null hypothesis as a 4 subdivided null hypothesis, one for nasal height, length, height, and breadth. Alternative, similarly. At least there is a mean difference between a pair of ears. Okay, then level of significance will be the same. Now the choice of statistical test will come. Since we have multiple variables at hand, we go with Manova. Okay, so Manova, and then inference will be drawn testing. Now, whatever may be the multivariate analysis you do, but while conclusion, it will boil down to a univariate analysis again. Okay, now most of you might be thinking that why this person has done the means and standard deviation without directly going for Manova. The summary statistics will help us to understand, okay, the nature of each characteristic, and basing on that, we can try to derive some of the observations and prior understanding whether there is a possible chance of rejecting the null hypothesis or accepting the null hypothesis. Okay, now let us have some kind of a note that seeing the nasal height, the main differences that we observe in 51.3667, 51.9667, I don't think so. There will be a difference between the nasal height of 150 AD and 200 AD. Similarly, if you just look into that 1850, 3300 and 4000, the nasal height, average nasal height seems to be very closer. So with my basic understanding on using the summary statistic, that is mean, I can have my own interpretation before having an evidence. I can have my own understanding that definitely nasal height, average nasal height has not varied across 5 different years of data collection. But now I have to verify the statement. Now, whatever the statement I got, I can define it as my alternative hypothesis, or null hypothesis. Okay, and then alternative, then alpha. Now we will go with Manova technique. Hope you are catching the flow, right? Okay. Now, similarly, Look into the length. 93.5, 94.5, 99. Somewhere, this mean length over 4000 BC to 150 AD is giving me some indication that there might be a significant difference, mean difference in the length of the Egyptian individuals. Okay. Similarly, coming to the height, not much of a difference, but breadth, yes, there is some sort of a mean difference. These are all just a perception. Okay, it's not an evidence. These are all the perceptions and basic understanding that we get out of the summary statistics. Okay, all these things we need to keep at hand well in before conducting the analysis. Now we go doing the Manova in SPSS. Now analyze general linear model. You have, when we take univariate analysis of variance, that is will come with Ankova or two-way analysis of variance. Okay. Now we go with this. Okay. One second. Yes. Now, this is general linear model and multivariate. Click on this. We get a dialog box like this. Send this year to the fixed factors and select all the variables and then send it to dependent variables. Okay. Now, if you want to take a plot, no, that will not come. Go to the post hoc. Okay, I'll come to this later. First, just let us run the basic Manova. And then what do you want to say? We can go with Cook's distance because to identify whether they have an outliers or not. I'm not interested now. Go to options, select year, display means per, year-wise means that you have already generated, descriptive statistics, and then just homogeneity test you can test to across the groups, and then continue. Now I'm doing a very basic Anova without any post hoc comparison. I'll come to that post hoc comparison later. We will redo the same procedure by adding additional argument of post hoc analysis. Okay. Now we got, see, the same table what we have generated that we got, descriptive statistics. Now, each year there are 30 data points collected. This is descriptive statistics that we have already had a lengthy discussion on this. And now we come to the multivariate test, which we'll talk about in accepting or rejecting the true distinction between the skulls. So we can go with Wilks lambda. So basing on this Wilks lambda information, what we can tell is there is a true distinction between the measurements across the years. Now the test between subjects will tell us with respect to each characteristics that is considered in the data across the year. Our focus point is this. Now look into this across year. When you see breadth, it's type 3, mean sum of squares, and F value is this, and it is significant. I said significant because I have a line of rejection, that is, if this p-value is less than 0.05, then it gives me a clear indication that I am about to accept the null hypothesis. What is the null hypothesis? At least a pair of years do differ with respect to mean breadth values. Now coming to this height, it is almost significant. technically. Okay, even length, it is highly significant. And coming to nasal height, sounds different. That is 0.203 is not less than 0.05. So what we do, we have to accept the null hypothesis. Now, bring back the discussion. What? Bring back the discussion what we had using summary statistics. Go back to this, where we are. Go back to this, summary statistics, where it is. Yeah. Now, nasal height, what was our perception by seeing the mean responses? We thought, I said that there will not be any difference in the mean nasal height across the years. That is what we observed, the insignificant p-value. Yes, the claim I made using the summary statistics has come to an evidence that the mean nasal height has not differed over the years. Again, go back to this. We thought of breadth and length, but we were in a dilemma whether the true difference of 133.6 and 130 does make a sense that mean height will also vary across the years. That was in a dilemma. But we got an evidence here that there exists a statistical significance between the years where the mean length, mean height, mean breadth do vary. Okay, so I'm trying to show you that don't straight away fall on the Anova table or Manova table. First, we need to develop or generate summary statistics. We need to try to dwell into that and make necessary observations out of that, and then come to the Manova table and see the p-value and try to relate them. Not only that, using the summary statistics, we will try to develop in what way we can define the null and alternative hypothesis. Okay, so that is the beauty in statistics, where the summary statistics, the data visualization will help us a lot in understanding the final output. Okay, right? Now the question comes, it's not yet over. It's not yet over. Okay, it's not yet over because I found statistical significance. I'm so happy because most of the researchers will tap their shoulders, will dance in a joy when they get a statistical significance. But now here is the main crux. When we get statistical significance, then the post-analysis has to be conducted. What is that post-analysis? Next questions do come like this. What are those things? In which year the mean breadth was higher, or what sort of years where the mean breadth or mean height or mean length was almost same or almost similar, right? How to answer these questions? Now we are trying to intervene deeper. Okay, we are trying to enter into the another layer of hypothesis testing, where once the significance is noticed in Manova table or Anova table, we need to venture out for further investigation. That further investigation is nothing but multiple comparison tests or post hoc analysis. Okay, what we call post hoc analysis. That is very, very important tool that most of the practitioners do not report, or even if they report somewhere, they will have some ambiguity to understand it in a proper way. Okay, some do well. Okay, now how to do that? How to address this? Now, how my hypothesis will get redefined? Let us take one simple characteristic, that is length. What was the main null hypothesis? The mean length is same across the years, but we try to reject it. That the mean length do differ across the years. Now take that hypothesis, frame the several sub-hypotheses across the years. How? In what way? The mean length differ between 150 AD and 200 AD, right? 150 AD, 1850 BC. 150 AD, 3300 BC. 150 AD, 4000 BC. What I'm trying to do here, I'm trying to make all possible combination where I can check in which pair of years the mean length has a variation and do not have the variation with respect to mean. Okay. Likewise, I am taking a pair of years one at a time, and I have 5 years. 5 C2. I get 10 combinations. 150 AD 200, 150 1850, 150 3000, 150 4000, 200 1850, 200 3000, 300, 200 4000. Similarly, you have 1850 3300, 1850 4000, and the last comparison comes with 3300 BC and 4000 BC. So we need to verify. That means we get 10 hypotheses. We get 10 sub-hypotheses to see whether the mean length do vary between these pairs of years. This is what we call multiple comparisons. Someone might ask, do we need it? Yes, of course, because the post-intervention will tell us how the mean characteristic or the mean of any variable has varied across different groups, across different treatments, how it will distinguish with another group. For example, coming to any biological experiment or any kind of even in education as well, you have a normal level of teaching, you have a blended teaching, you have only online teaching. Now you wish to compare among these three, whether blended worked very well to reach out the students, whether the usual offline mode has worked out, or usual online mode has worked out to reach out to the students. Okay, so here we will be having control and the offline and blended, offline and online, blended and online. Hope you are getting, right? So this is where we need to have a post-intervention analysis to see how the mean response, the mean scores achieved with a different mode of teaching environment. Okay, now let us try to do that, and then I'll take some 5 minutes to interact with you after that. Now again, go to this general linear model, multivariate, and now you have to choose the button post hoc. Now select that post hoc. By default it is selection. In selection, select that and send it to the post hoc test pan. Once you do that, we have a small bunch of post hoc tests, like least significant test, student Newman-Quelz test, Bonferroni, Key, Shidak, Scaffi, Duncan's, Dunnett. Okay, like this you have other things. Now, when we have equal variances assumed, we go with these tests. When equal variances are not assumed, we go with this. But most often we assume that we do have with equal variances assumed. Okay. Now let us try to click on the Taki, because it will control one of the important error rate that will get observed in doing post hoc analysis. That error is what we call family-wise error rate. Very, very important concept that most of us, even I learned after many years of this data analysis training. Okay, so this Stucky test will control that family-wise error rate. What do you mean by family-wise error rate? That we will see by the output. Control, continue, and then click OK. Now, straightforward, I'll go to the post-hoc test outcome. This is what we get. Let us take the at least honestly significant different test. HSD. The another name of Tucky's test is honestly significant different tests. Okay. Now, these are all the combinations. Repetitive combinations will be there. We can remove them when they are already repetitive. Like, see. Now, let me go to the length. Wait. See, again, you started typing good morning, all this thing. We are almost nearing to noon. Okay. Wait for your queries. I'll be interested in having some questions. I'll try to understand. I requested you to stop telling all these things. It is interfering me. Okay. Now length. Let us take the length. 150 AD to 200 AD. The p-value is 9.926. Now the question comes. What is my level of rejection? Is it 0.05? No. It is 0.05 by the number of groups at comparison. Number of groups at how many groups are at comparison? 5. Now your new p-value, which will be deduced, is 0.05 by 0.05 by 5. That is 0.01 is your new p-value. Because why we need to take that? Because the main hypothesis is splitted into 10 sub-hypotheses. This 10 sub-hypothesis becomes a family of hypotheses related to the main hypothesis in the Manova. Right? So, the same p-value will not be taken into consideration. That will be divided by number of groups at comparison. So, this 0.926 should be compared with 0.01. Not significant. 0.273 with 0.01, not significant. 0.000, 0.01, yes, significant, that's good. And 0.000 with 0.01, yes, that's good, significant. Now, what does it mean? Significant, significant, not significant. Significant means that the mean length do vary across 150 AD and 3300 BC. Now, varying is fine. In what way? Whether the length has decreased or length has increased. I need to tell that. That is the final output. To do so, see this value. What this value stands for? This is what we call mean difference. The mean length which is observed in 150 AD will be subtracted from the mean length of 3300 BC. So that mean difference is 5.566. Now the sign it has is minus. What does it mean? The mean length which is observed in 150 AD is smaller than 3300 BC. So there is a reduction in the length of an individual over these generations. Now we are converting our numerical information into a practical insight. The negative sign indicates that there is a mean reduction in the length from 3300 BC to 150 AD. Similarly, 4000 BC as well. So this is what we need to write. Just think of doing a small analysis, adding small technique, concepts like mean standard deviation, post-hoc analysis, Manova. These numbers are making us to talk voluminous of information out of a simple 150 sample data. That's why I believe as a statistician, I believe data makes us to speak a lot, and it will help us to scribble out beautiful insights that will be taken from summary statistics alone, that mean difference, mean and standard deviation. Okay. Similarly, if you take the nasal height, everywhere, where is that nasal height? Let us go to the nasal height, the contradictory part. If you see the nasal height, everywhere the p-value is insignificant. So the mean nasal height has not varied much. Okay, it's not static, but there is a difference. But that difference is not a pivotal thing to be notified that this difference is a claimable difference with respect to mean nasal height. What I'll try to do here is I'll try to give you interaction time for 5 to 10 minutes on this Manova and related questions. Then we'll move to Ankova. Okay. Now the floor is open for discussion for 5 minutes. Okay. You can start in placing your questions in the chat box. Again, 11:30, I'll start the another concept.
Participants, you can post your question in the chat box for your clarifications. Other than that, you don't give good morning, good afternoon, those messages not encouraged.
Hope I made it clear, everyone, about the technique of Manova, its assumptions, how to conduct in an SPSS, and how to make use of the summary statistics, Manova table, and post hoc comparison. Okay, any questions on this? Okay, how can we address the summary statistics in the article? Yes, that will, this is how I said, one by one, one by one, one by one. See, don't please type the numbers, your registration numbers. It is pulling out the questions. Okay. Okay, now, yeah. Summary statistics will help us a lot in taking, I mean, just now I gave an example that the mean nasal height was not varying much with respect to, there is a small difference in the decimals. Likewise, if it is concerned to your experiment, you can take out. Okay, similarly. Let us take, now I have taken body mass index, heart rate, and sugar levels across control, cycling, and treadmill. I got mean body mass index in the control group as 23.1, in cycling group as 22.7, and in treadmill, I got around 21.5. Now, the mean things will make us to have an emphasis on perception that 21.7 is somewhere having some difference with respect to the control group. So cycling might benefit to make the people to maintain their normal body mass index levels. So the numerical quantity with respect to the mean or mean difference will help us to reach out to the domain area. Yeah, next question is, when could you please again explain when to use Manova? See, when we have multiple variables at hand and are to be compared across more than two groups, then we use Manova, like heart rate, sugar level, body mass index across control group, cycling group, and treadmill group. Then this is things. I think people have missed the first initial things. Okay. Yes, Venkatrao has raised the question. Dr. Venkatrao, that could you explain about bootstrapping in Manova? Wonderful question, sir. Yeah, bootstrapping is one of the resampling technique that will help us to mimic the same kind of a comparison for multiple number of times. Okay, when we take this bootstrapping, when we have to go for bootstrapping, when you have a limited sample, again, your experimentation will not allow you to procure some more samples. you have only limited samples to do, or your experiment is very precise and cost effective, you cannot repeat it multiple number of times, then the statistical technique, which is called resampling procedures, will come into our help. So bootstrapping is nothing but randomly selecting the data points which are available with us, maybe 50% of them in each year. Let us take the Manova itself. Okay, we have 30, 30, 30, 30. I want to run 100 bootstrap to see whether the consistency exists with respect to the mean parameters of these four variables. Okay, then what I do, 50% samples I take from each parameter across each year, then I do bootstrapping. We can do that to see the bias should be minimum, and to see how far the mean consistency is observed. Okay, hope I answered your question. Now coming to that, how can we apply it to two variables? I didn't get your question, Dr. Manjusha. Can you please elaborate it? Explain hypothesis framing once. See, hypothesis framing we can do with two perspectives. Okay, one perspective is with respect to your objective. Okay, when we start your study. The other perspective is we can define our own hypothesis by using the mean and standard deviation. In the nasal-light example, what we witnessed is by seeing the average nasal light across different years, we try to make a perception that the decimal differences might not show a significant impact. So this is how we started framing the null hypothesis. To whom the p-value has to be compared as well as the last table is concerned. To whom means, I mean, with what? This p-value is between observing between whether the mean nasal light vary between 280 and 150 AD. This is our line of selection, decision making. Okay. Now, this 0.949 should be compared with 0.01 because we have 5 groups under comparison. That 0.05 should be divided by 5 groups, so we get 0.01. Okay. Now, we'll move to next question. Can you explain 0.0? Yeah, just now I did Ravindran ji. Okay. How differ from Anova? I have already answered this. This also, Sanjay, I have already explained when we use only one-way Anova. When we have one factor, that is control, cycling and threading, this is called factor with 3 components, 3 groups. And only heart rate is measured, that will become one-way Anova. Along with heart rate, you measure cholesterol, you measure triglycerides,
1 minute, sir. We will connect you. 1 minute. Yes, sir. 1 minute, sir. 1 minute. Ravina madam. Ravina madam.
மேடம் சொல்லுங்க மேடம்.
மேடம் யாரும் லைன்ல வரல பாருங்க. சாரா கோஸ் ஆக்கணும்.
ஆமா மேடம் சொல்லிட்டேன்.
சொல்லிட்டீங்களா? ஓகே ஓகே.
சொல்லிட்டேன் மேடம். ஜேபிக்கு கொஞ்சம் கால்
சாயிலா,
பண்ணுங்க.
மேடம் சார் கோஸ் ஆக்கணும் மேடம்.
இந்த வர. Yes, sir. Sir?
Yes. Thank you, madam.
Okay, sir.
I'm sorry for that internet issue.
No
Okay.
problem.
Yes, we need to check the assumptions, but I have not done that. And I assumed that the data follows normality. And if you see this mean and standard deviations of whatever the data I have taken, okay, whatever the data I have taken, where is that? Yeah, whatever the data I have taken here, we can see this the standard deviation is too low. Okay, so that itself would indicate that data is normal. With this mean and standard deviation will help us a lot in different perspectives. With different perspectives. Okay. Right. So do you have any questions? Because I lost all the chats since I was I mean due to the connection, I lost all the chats. Any questions on this slide? Madam, can you enable chat for 5 more minutes? Thereafter you can close it.
Yes, sir.
அங்க இருந்து திருவாரூர்ல நான் போன் அடிக்கிறேன். சாயிலா அடிக்குது. நானே போய் இருப்ப கட் மாதிரி போட்டேன்.
Yeah. Yes, you can avoid intercept. You can just report what we say this. You can report this alone. You have to report the week's lambda of this year, and you can report the F values corresponding to F1 P values corresponding to the year. Okay, no need to present the entire table. This is our main area where we need to take a decision. Is it enough to check mean and standard deviation for normal? Not necessarily. This is kind of a thumb rule. Okay. It is a kind of a thumb rule. That is, mean and standard deviation will give us an indication. Okay. You can apply a box plot. I can show you here. You can apply multiple box plots. Okay. Box plot summaries of separate variables. I can show you here. Boxes represents okay. Okay, 1 second. The graph is being generated. Once the graph is generated, we can, yeah, we can show you that. See, this box plot is another indication of normality, that in almost all the, I have taken the overall 150 samples. Okay, if there are total 150 samples, then I have taken 150 samples data here. The median line is at almost near in the center. So that itself is indicate that the data is normal, but there are one or two outliers which may not affect that much, but we need to take into account of that also. Okay. Yes, yes. If there are 6 groups, we need to divide them into 6. Okay. Please give me an example defining use of Manova in experimental research. You can tell one experiment of what you are doing or related to that. I can easily make you understand. Okay. No, 0.05. 0.005 should be divided based on the, 1 second. What is the 0.0505 should be divided based on the number of groups. If it is more than 2 variables and no. Even in Anova also, when you are comparing more than 2 groups, you go with Anova, Manova, Mankova, right? So in all such techniques, in the post hoc analysis, only particular to post hoc analysis, we have to use the 0.05, not 0.005. It is 0.05 by the number of groups at comparison. Okay. What is the alternative for Manova for non-parametric test? I don't think so. There exists an alternative. What do you say? Alternative for Manova. Anova, we have Kruskal values. Repeated measures, we have Friedman test. Manova, we don't have. I think so. Yes, we don't have. At the end of the session, could you demonstrate how to copy Spss output and graph, paste it into Word doc? Okay, fine. Now itself, I can show that since we have developed too many outputs, let us try to show the same thing. Let me try to remove some things. I don't want all these things. Okay, now what you have to do is select this output. Okay, select this output and then click this icon. This is what we call export. Okay, click on this icon. It will show you this output wizard. You want objects to export all visible selected. Let us take all by default. Now, always I suggest you to save the output in Excel file rather than Word. What happens? No, the mean standard deviation table, when you have more than 4 to 5 groups, it will go in a layout, a very horizontal layout. So in Word document, it will be very difficult to edit it. Hence, so it is always suggestible to go with Excel and then choose where you need to save. Browse this. Let me try to browse, and I have saved a file called desktop and then education. And here I can give a file name, results of Manova or whatever the experiment you have. Save it. And then open container. Once you export it, show me the file where I have chosen this path. Then click OK. Now the exporting process is on. It's going on. Everything will come out. Okay, even figures, everything will be exported to thing. Now see, I have to share another thing. New share, where is this thing? Yeah. Now if you look into this education, hope you are able to see results of Manova is there. Now from here, I can easily, because Excel is a self-formatting, we can easily do all the editing process and then make it into Word. That is what I suggest. Okay. Right. Hope I have clarified the doubts as of so far. And can we move to Manova? Manova, I think we have done. We go with Ankova. Okay. Yeah, let me try to remove this since I have done it. Now open. I have already have some Anova data. Okay. What is this? Let me check what file name I have done. Oh, okay, fine. This is another thing where I can show you some other aspect. I'll try to show you in different way this time. Hope you are able to see this highlighted Manova, right? Now, if I double click on this, I'll get a notepad file like this. Now, how to take this and select? Okay. Now, Control A, select this. I'm opening an Excel file. I'm opening an Excel file. I'm pasting here. Okay. Yeah, this is my Excel file. Now, when it is taken from thing, already it is placed into different cells. I can select all the columns and double click on this. We can do auto fit. That is what we call auto fit. And now this is one data I have on experimentation. This is what we call replications in a design. And the product yield is my response variable. Okay. And optical density is another variable. And dry weight is another variable. And nitrogen source, ammonium chloride, and you have yeast extract. Okay, and temperature at different temperatures, the product yield is verified. That is 30 degrees centigrade, 35, and 37 in both the combinations. Now, what we can do with this is first, in order to export that, we need to have a proper data coding. Let me do it fast. Control F, 30, replace it with 1. Okay, and then you go with 35, make it 2. And then you have another temperature called 37, 30, and code it as 3. That's fine. Now we need to replace this into Control F. Ammonium chloride, I'm trying to make it as a code 1. And in order to overcome the spelling issues, let's copy this and select the control complete column and paste it here. And this will become 2. Replace all. Now we have converted almost all the categorical information into thing. And otherwise you can do insert a comment. Okay. 30. 1 as 30. 2 as 35. 3 as 37. It will be forever. No one can save it. Okay, let me save this. Okay, now similarly, I can create a comment. One as ammonium chloride. Number 2, I have yeast extract. Okay, save this. Now, once we are done, let me see across product yield. Okay, I am interested in this product yield. Okay, this is my response variable. And if I want to compare product yield across different temperatures, okay, I can make a note here. Compare product yield. This will answer my, this will answer your questions. Few of your questions already raised. Compare product yield across different temperature. Then we use Anova. Okay. Compare product yield, dry weight, optical density, or we can take dry weight across temperature. Then we use Manova. Okay. Now compare product yield across temperature, but using dry weight as covariate. We use Anova. Now compare product yield, optical density across temperature with dry weight as covariate. Okay, we use dry variate. We use Manova. This is the clear distinction difference between each technique. One variable across more than 2 groups is Anova. More than one variable across more than 2 groups is Manova. And now we are dealing with the third one, that is one variable, but the another variable will be treated as a covariate. But we have more than 2 groups. Then that technique, which involves covariate in comparing a particular variable across different groups, that is more than 2 groups, is what we call Anova. What is the role of a covariate? How do we identify a covariate influence? The another name of covariate is what we call confounding variable, or a hidden factor that might affect the response. When we do some experimentation, when we do some sort of a study, okay, the hidden factors will have a lot of influence, on the outcome, which we may not understand at the initial stage. For example, if you want to, let us take an example like the same cycling treadmill, okay, cycling treadmill and control groups. I want to observe the body mass index, or I want to observe the heart rate. Now, there should be a common age of people. On which age group you are doing the study? Or there should be common people who should not have a problem with spine. There should not have a problem of heart-related cardiac issues. Likewise, when you filter out, okay, particularly let us take age is one of the factors. Are you trying to do the adolescent age, or are you trying to do within the plus 45, something like. So age can be influential variable in the response. Can be influential variable in the response, or the food intake, the calorie, the protein, the carbohydrate, the intake will also fetch to the control of body mass index. So a covariate which influences on the response variable some way or the other, okay, is treated as a confounding variable, okay, as a confounding variable. So this is what we call. And obviously, when we deal with more than one output response variable, then that will become multivariate. Still, we may have a covariate structure into that. So that is what we call Manova. So here, this example, so in this example, what I try to do is, this is my response variable, product yield. Okay, let me shade this for understanding. Now, when I went down, okay, I was not able to figure out the title, right? So better we can create a freeze span so that we can freeze the first row, top row. Now, whatever the level I go down, I will be able to see the heading. Okay. Now, I'll treat this dry weight because the product yield may depend upon the dry weight. I assume that. Let me take it as some influential variable, and my group at comparison. Group at comparison will be taken like this, and let me put it into a different. Okay, so these three variables I'm trying to do. Now let us take this data into SPSS, and then we'll go for better understanding. Okay, now I'm trying to load the data into SPSS. Yeah. Where is the data? Yeah. Open star.ca XLS. And then where is my data? Complete data, Anova. Here it is. Open. Now, which file, which Excel sheet I have my data? It is in sheet 1. Okay. Now we have certain codes we have given, right? Now temperature, value labels, I can write it as temperature, source and replications. And value labels, what is 1? It's 30, 2, 35, 3, 37. Now, what is N source? It is ammonium chloride. 2 is yeast extract. Okay, I think let us save this data. That is the best practice to do. Uncover data. Now we have saved this. Now let us try to look into a basic analysis, that is frequencies. You want to see the frequencies? Yeah. Okay, let us try to develop the means. Okay, how to do that? Compare means and means. Dependent variables are dry weight, optical density, and product yield. Okay, and then across temperature. Now I'll make it in a different way. I have one more influential categorical information, that is ammonium chloride and yeast extract. Now I'll create a layer. Now send that N source to this independent list. Now by default, means and standard deviations will be there. Click OK. what I'll get, see, this is the 130 temperature and ammonium chloride. The mean dry weight is observed to be 5.453. And in total, in temperature 30, the mean dry weight is 5.92. Now let us make it more meaningful, handy enough. Pivoting trace, and I'm interested to put this and source on the top of the variable. I think this will be quite easy, right? I can remove this n. I don't want the n here. I can remove this total also. I mean, as of now, I'm not interested in total. Okay, let us keep that. People will get confused. Let me keep that. And then okay, now the table has reduced. Okay, now it's clearly seen that in ammonium chloride, the dry weight under temperature 30 is 5.45 with a standard deviation of 1.6. The same dry weight with ammonium chloride focus at temperature 35 is 5.95. Similarly, at 37 is 5.85. Overall, irrespective of the temperature, under ammonium chloride, the dry weight will be, mean dry weight will be 5.75. Similarly, optical density will be 1.73. And this of the product yield will be 41 point. But I am interested across each temperature. So let me take a look here. It is 5.92 at 30 degrees centigrade overall. And if you see this between optical density and yeast extract, I can convert this data into a different perspective. If I want to compare ammonium chloride and yeast extract to see how the dry weight, optical density, product yield individually they vary, I can do 3 independent sample t-tests, or I can do Hoteling's t-square test. Okay, I can do two-way Anova. Okay, if I take dry weight as a covariate, I can do Ankova. I can do Mankova. This particular data set will help us to understand t-test, Hoteling's t-square test, F-test, Anova, Ankova, Manova, Manko. The same data set for an understanding purpose, and it purely depends upon the principal investigator's knowledge, how to make use of the variables. So accordingly, we can dwell into that. Okay, so the mean the mean optical density is our mean product yield at the temperature 30 in ammonium chloride is lesser than the mean product yield under yeast extract at the same temperature. So yeast extract, because of the influence of yeast extract, the product yield is higher at the same temperature 30. If you look at as increasing the temperature, the 69 to 72 it has come, and then it has come to 75, nearing to 75. So an increasing in 5 degrees or 2 degrees centigrade, on an average, the mean increase is around 2.8 units. 2.8 units. So likewise, this means I stress more on the mean standard deviation, because that will help us to write the interpretation very properly, connecting to the outcome variable. So, yeah. So similarly, at the 37 degrees centigrade, the dry weight is 5.8 under ammonium chloride, and the same it is 6.58. So in total, what you are witnessing now, with respect to the N source category, that is yeast extract, the mean values of dry weight, optical density, product yield are at higher levels at each temperature value. Is it so? Right? Okay, so the mean dry weight, mean optical density, and mean product yield are comparatively having the higher values in yeast extract when observed with, I should not use compare because we have not done any comparison, when observed with ammonium chloride values at each temperature. See, that means just the mean table has given us a kind of a description, a narration that how the variables behave when we have done with yeast extract, when we have done with ammonium chloride. Okay, right? Right. Now, we'll try to do, yeah. Now, we'll go to data view here. Where is this? No, I don't know if we close this. Yeah. Now, when I take product yield and compare across temperature, okay, I can do Anova. Okay, scaling is faster. Yeah, this will Anova. If I select optical density, this will become Manova. Okay, if I choose dry weight as a covariate, then it will become Mankova. If I remove this optical density, if I choose only product yield, dry weight, and temperature, it will become one-way Ankova. Okay, let us do that. Analyze general linear model. Okay, analyze general linear model. Analyze general linear model. Univariate. Dependent variable. Here itself we are restricting. See, only this span allows only one variable. This span will allow only one variable. So that is product yield. Send it here. Fixed factors, you can send it temperature and covariates. Okay, if I feel optical density will influence the product yield somewhere in a hidden experimentation, then I can take optical density. But I feel the dry weight might influence in the covariate. I'll take that as a covariate. Okay, now go to options, select the temperature, display means for temperature, and we can parallelly compare them across each temperature with, we can compare the product yield across temperature levels, and the comparison what I'm trying to take is Born-Foronis comparison. Okay, now let me create the descriptive statistics and the estimates of effect size. These two things we need to select. Okay, estimates of effect size, and then click on continue button. And finally, just press OK. So we get list of tables every time, but we need to be careful in taking them. This is not fine because I'm not interested, because we know that is a fixed how many samples in each temperature and how many samples in what is the mean. Now we have descriptive statistics here and we have estimated marginal means here. What is the difference between? I'll tell you. This descriptive statistics is in general. It is not adjusted with the covariate. Okay, we have considered a covariate, dry weight. These means are unadjusted summary statistics without considering the covariate. So if you see this product yield is 56.53 at 30 degrees temperature, 56.47 at 35, 58.25 at 37. And now coming to the temperature, look at the p-value, 0.001. Now what is the level of significance? What is the hypothesis here first? the mean product yield do not differ across the temperature levels of temperature. The alternative is there exists a difference, mean difference between the product yield across 3 levels of temperature. I choose the alpha level is 1 second. Okay, I choose the level of significance as 0.05 and test statistic I have done already. It is Anova and inference is based on this. 0.01 is less than 0.05. We claim that there exists a mean difference. There exists a statistical mean difference between the temperatures with respect to product yield. Okay, or the mean product yield do differ across the 3 levels of temperature. That is one part. Second part is about 0.009. Even dry weight, which is taken as a covariate in the model, has a significant result. Means the product yield is getting influenced by a hidden confounding variable, that is dry weight. So we need to account for such intervention variable. We need to account for such intervention or confounding variable before directly you estimate the product yield. Okay. Now we'll come back to this estimated marginal means. Where is this? Yeah, estimates. So these are, now you see, these are all called estimated marginal effects. Means these means are estimated by adjusting the average dry weight of 6.026. Means it is a regression model. Now you fix the dry weight at 6.237 and then vary the temperature, you will get the response. What is the response variable here? It is a product yield. It is a product yield. So this, you have fixed it. This is a controlling factor. So you have taken an estimate of the dry weight so that it can add its influence in the outcome variable. In the outcome variable. Okay. Now, yeah, the post-hoc comparison showed insignificant result. So the average when adjusted for based on the marginal means. So when using these means, that is 56.68 and 56.58, there is no much difference, 0.10 and 58.04, even that is minus 1 point something, is a negligible value when it's taken for product yield at the 3 different levels of temperature. 3 levels of temperature. So based on the estimated marginal means, it is witnessed or it is observed that at all possible comparisons of levels of temperature, there is no difference in the mean product yield. There is no mean difference in the mean product yield. Okay, so this is how we go with doing analysis of covariance. So what we try to do here is actually we try to do some of the observations where whether the variable which can be influential will affect the overall outcome or not. So this is what we inquire in Anova, and we have done the post pairwise comparisons as well. Okay, pairwise comparisons as well. Now let me extend this to multivariate, where you have optical density and product yield into dependent variables, and dry weight as a covariate, and temperature as a fixed factor. You can go to options, temperature, display means per, and you go with one for only. This reduces the family-wise error rate, and descriptive statistics and estimated effect size. So this descriptive statistics and estimated effect size will be developed, will be computed for both optical density and product yield, adjusted for covariate dry weight. Okay. Yeah. Now what I'm trying to do, I'm trying to extend the Anova version to a Manova multivariate, because I'm using two variables which are response variables, that is optical density and product yield. So that is what we call a multivariate, more than one variable setup with a single covariate, that is a dry weight, and these two response variables are observed at 3 levels of temperature. 3 levels of temperature. So these are all the means of optical density without adjusting for dry weight. Okay. Now we will come that adjusted values at the bottom. Now the covariate is significant, dry weight is significant, that has its confounding effect on optical density and product yield. But temperature is not significant. See, Wilks lambda closes to 1. Whenever the Wilks lambda approaches to 1, it lies between 0 and 1. Wilks lambda approaches to 1, it has insignificant outcome. So temperature do not differ, but there is an influence of the confounding variable. Influence of the confounding variable. Now this is the Manova table. This is the Manova table. Okay. Now if you see the temperature here with respect to product yield and optical density, it is significant. Okay. And dry weight with respect to optical density doesn't influence much, but optical product yield, it has its high impact. Okay. Now how to understand that? We come to the marginal things. Now if you see this, covariates appearing in the model are evaluated at the values dry weight is equal to 6.0237. So this 1.929 or 1.997 and 2.00. See, if you take the mean difference like 1.92 minus 1.99, 0.07. The 0.07 is called the mean difference, and it is very negligible, and it is resulted in insignificant p-value. Okay. Similarly, if you see this with respect to product yield also, mean optical density and product yield, when adjusted for a dry weight at 6.0237, they do not differ much. They do not differ much. Suppose if I do the univariate analysis by removing the covariate structure. Okay, I am doing Anova here. By doing Anova here, see, temperature is significant. And what about the pairwise comparisons? Is again with respect to the is insignificant. Again, is with respect to significant. Okay, so this is for just how to do one-way Anova. That doesn't have an thing here. Likewise, the same data can be used for multiple purposes. I already showed you several times. how the single data for illustration purpose we can have we can use multiple techniques. Okay, so I open it for discussion for last 5 to 10 minutes, then we can wind up the session. Okay. You can enable the chat. I can take question by question. I'll try to answer in 5 to 10 minutes because I have some meeting at 12:30. I have to move fast to the thing. Okay, so I can click on stop sharing. Now, questions, please. If you have any, don't put your register number, don't put your address. If you want to interact with me, you can interact with me at my mobile number or this is my email ID and this is my mobile number. Okay.
Participants, kindly give in your questions only, not a RMSA number and all. Any clarification, you can give it in your chat box.
So you can mail me if you have any clarification. If you need any clarification in your studies, or you can message me according to that. Okay, I'll be comfortable enough to interact with you. No hesitations. Okay.
We know that the session was very informative and it was a nice presentation. Your opinions will be considered later. Now you ask your questions.
Yes. Which statistical technique? 1 second. Which statistical technique can be used if 2 experimental group and 1 control group? Oh, wait. One control group on health related like BMI, endurance, flexibility with the pre and post. Okay, so you need to go with Manova by taking the difference of pre and post. If you want to consider only the post, okay, I'll put this way. First solution is take the difference of pre and post, and you will get a differential value. Use the differential value and apply Manova. Okay, apply Manova because you are taking BMI, strength and endurance flexibility. Okay, since you have more than one variable, you go with Manova. Now, the second option, in case if you feel that the BMI strength or endurance flexibility will influence or might influence at the post value, then you treat those pre-values as covariate and apply Manova. As a practitioner, you need to decide. Okay. Then oh my God, too many questions here. How to differentiate for covariate and factors involved? Covariates are continuous measurements, continuous variables. Factors are categorical. Like in our example, we have taken what was temperature at 30, temperature at 35, temperature at 37, or treadmill, cycling, and the control group. These are all called factors. Covariates are a quantitative characteristics. How alpha will be consumed if we use multiple comparisons at a time? See, alpha value, as I said, when you go for multiple comparison, based on the number of groups at comparison, you need to divide the alpha and make use of this. Okay. What is the difference between mean and LS mean? Can you elaborate that LS mean? What is the main difference between Manova and Manova? See, that's what in the example recently posted by one person. They want to test this BMI strength and endurance flexibility across 3 different groups. That will become Manova. If they want to use the before starting the study, they have recorded the BMI strength and endurance flexibility. Then if they want to make use of that information as a supplement input to compare the post values, then that will become a covariate. Then that study will get converted, study design will get converted to Manova. How to use Likert data in Manova and Manova? Okay, generally, one assumption is that most of the things we need to go with the quantitative characteristics only. Okay, quantitative characteristics only. A Levin's scale is for comparing homogeneity of variances across different groups in ANCOVA. Okay. Am I muted? No. Okay, I can suggest some book on SPSS. Most of the time I read on discovering statistics using SPSS. Okay, that is one textbook, discovering statistics using SPSS. The other book is Handbook of Univariate and Multivariate Analysis using SPSS by Robert Hope. Okay, and Multivariate Statistics Made Simple, a practical approach by K.V. Sharma and R. Vishnuvardhan, myself. Okay, these three books will be handy enough to make you understand. If you want to give priority, you can give. I can give priority to my book because it is purely demonstrated with live exam. Sir Venkatrao sir, you can connect me. We can discuss, and I'll try to make your query more reasonable and meaningful. And this is for Dr. Venkatrao. Okay. I think somewhere I lost my flow. If you want to take, then that will become repeated measures Manova. Because if you want to take more than 2 time points, it will become repeated measures data. You need to go with repeated measures Manova and repeated measures Anova with a single variable. Okay. I'm typing the textbooks based on your request. Multivariate statistics made simple. A practical approach by K.V.S. Sharma and R. Vishnuvardhan. This is one book. The other book is Handbook of Univariate and Multivariate Statistics using SPSS by Robert Ho. And the other one is Discovering, let me check the authors. Discovering Statistics using SPSS. This is also a nice book. I loved it. Discovering Statistics using SPSS by Andy Field, I think so. Yeah, Andy Field, correct. Andy Field. Okay, so you can, again, I'm trying to give you, again, you can reach me out. I have, with my experience, I can help you out in your things. Collaborations are also welcome. I'm basically applied science, applied statistician. Okay, you can also collaborate with me for better statistical reporting. Okay. Experimental design is nothing but this one. Repeated measures design only, it will come. So the statistical technique we use is one-way repeated measures Anova or one-way repeated measures Manova. Okay. And I encourage collaborations. You are most welcome. Whatever may be the discipline, because statistics is live in almost all feathers of science and engineering. So thank you so much for patience listening. And I thank the organizers for giving this an opportunity, wonderful opportunity to interact the listeners across the country. I think so. Okay. I'm so thankful to the HOD of the department, Ambedkar sir, and the organizers, Dr. Sai Leela, and other faculty members related to this event. I am so thankful.
Yeah. Sir, 1 minute, sir.
Yeah,
We have the formal vote of thanks. Susila, madam.
Yes, madam. I'm here only.
Now I request the organizing secretary, Dr. Susila, madam, to give the formal vote of thanks.
Yes, madam. I'm audible, madam.
Yes, madam. Yes, madam.
Ladies and gentlemen, very good afternoon to everyone present here for the IQAC enabled 2-week online international workshop entitled Research Methodology and Statistical Applications SPSS for Social Sciences. So today, 27th July 2021, the session was handled by Dr. R. Vishnu Vardhan sir, Assistant Professor, Department of Statistics, Pondicherry University, Puducherry. And San has explained about Manova, Ankova, and Mankova with the examples, theory, and applications in the research. The first one, part one, is Manova, is a technique which determines the effects of independent categorical variables on multiple continuous dependent variables. So it is usually used to compare several groups with respect of multiple continuous variables. Sir has explained with the examples also. She has explained its assumptions, how to conduct by using SPSS package, and how to compare with the groups. That is, he has explained with examples. So that is the BMI, heart rate, and blood glucose level, and other variable treadmill and cycle group. So post hoc test also, as I explained, framing of hypothesis based on the perspective level, then differ from Anova and explained with examples. That is measure only heart rate like this. Sir has explained the part two, that is Ankova. So that is used in examining the differences in the mean values of the dependent variables that are related to the effect of controlled independent variables while taking into account the influence of uncontrolled independent variables. So nicely has given a difference between all these one, Anova, Manova, Ankova, and Mankova by using examples ammonium chloride, compare product yield across different temperature. We have to use Anova, compare product yield, dry weight across the temperature. We have to use Manova, then compare product yield across different temperature by using dry weight as covariate. We have to use Ankova, then compare product yield optical density across the temperature with the dry weight as covariate. We have to use Mankova. Nicely has explained. I think all the participants can get benefited, and the SAR has demonstrated by using SPSS package with examples also, case processing, summary report, everything, sir, and explained the descriptive statistics with the examples, test for between subjects effect based on the estimated marginal means. So post hoc comparison also. Then part 3 has explained Mankova, then used to test the statistical difference of the effect or one or more independent variables on set of 2 or more independent variables. That is demonstrated multivariate test also. Sir, salute, sir. Thank you so much for your for sparing your valuable, precious time. And I hope the session was the most intriguing, and that it will undoubtedly benefit to all our participants, and by especially our research scholars, research academicians. I thank all the participants for attending this program continuously and clarified all the doubts with our today's resource person. Thank you very much, sir. Thank you, participants.
Thank you. I am so happy that the as a collective effort, the organizers have brought all the good people. Every day I'm just joining the sessions. I'm listening to them. Okay, everyone is detailing out very fantastic. Okay, so that's effort efforts, and my congratulations and greetings goes to the team. Okay, thank you so much.
Thank you, sir. Thank you, sir.
Thank you, sir.
Yeah,
Thank you, sir, for your words of appreciation. I am sure it will motivate us to do much more better, sir. Really.
Yes, yes,
yes, sir.
Thank
you, sir. Thank you, sir. Very nice.
Thank you,
Thank you, madam. Thank you. Yeah. So,
as a faculty, we learn
now?
more, sir. We learn more. As a faculty point of view, we have learned more. So not only for our research scholars, upcoming researchers, as well as faculty, for example, might know. So I'm very interested in this subject. For that only I took this part for the last 2 days I'm giving.
No, your elaborated summary itself shows how much
that
you are
is,
interested.
we have to give the respect to the resource person, sir.
Thank you. Thank you.
Thank you, sir. Thank you.
I'm leaving the meeting. Okay.
Yes, sir. Yes, sir.
Saila.
Thank you, madam. Thank you.
Susila madam, very nice.
Thank you, madam.
Salutations for you also.
Thank you, madam. Thank you.
Yes, madam. Susila madam. Thank you.
Thank you, madam. It's all our team efforts. அதெல்லாம் ஒண்ணு இல்ல மேடம். எனக்கு சப்ஜெக்ட் பிடிக்கும், அதனால உட்கார்ந்தேன். வேற ஒண்ணு இல்ல.
Okay, thank you, madam.
Thank you, madam.
Bye.
Shall I leave, madam?
Yes, madam.
Yes, madam.
Thank you. We'll meet tomorrow.
Thank you. I am also leaving. Thank you.